Hey guys, in this video we're going to continue to look through examples of verifying trig identities, but specifically leaning on those that involve algebraic techniques such as multiplying by conjugates and factoring and just making simple substitutions. And so let's go ahead and take a look at, just starting with number one here, kind of some of the patterns that I'll have you guys looking for on your own. And I suppose that looking at number one, I would definitely work on the left-hand side first. It looks like the more complicated side. Now I notice on the left-hand side, I could try to make some substitutions here, like cosecant is 1 over sine. I'd have a 1 over sine here, but it doesn't lead me very far before I figure out that that's probably not going to work for me. So looking at this, the thing I would point out is that there are two terms in a difference with one another. And the fact is that these two terms have a common factor. So one thing that I always want us to be looking for is a greatest common factor, or just any factoring patterns with algebraic or trigonometric expressions. So in this case, I'm actually going to factor out the cosecant out in front. So the cosecant of theta would come out in front, and then the expression that would be left on the inside would be just a 1 to take the place of where this cosecant was before, minus the cosine squared of theta that would be left if we factor out the cosecant. And in this particular case, that would be nice to get, because recall that sine squared plus cosine squared equals 1. That is, sine squared plus cosine squared equals 1. So 1 minus cosine squared is just our sine squared here, and that's kind of nice, given that we are about to take then a sine squared, which we're substituting in, I'll put parentheses around it, times a cosecant. And knowing that cosecant is the reciprocal of sine, then maybe this is the best time to make a substitution in terms of sines and cosines for the cosecant. So 1 over sine squared times, and I suppose I'm going to write a sine squared theta over 1, just to go to show that this sine is going to cancel out with one of these sines here, and it leads us to just having a sine theta left on the left-hand side, which is wonderful, especially given that that's what we were trying to verify in the first place here. So since we did verify what we were trying to verify in the first place, we'll write QED. Okay, going on to number 2 here, taking a look at the left and the right-hand side. Now I'll tell you, I would be tempted to call the left-hand side the more complicated of the two sides, but in this particular video, one of the things that I want to point out to you is a lot of the time we're going to be multiplying, doing what's called multiplying by the conjugate, okay? And so that is, looking at the right-hand side here, I notice that the top and the bottom here are kind of like this 1 minus sign, 1 plus sign kind of thing going on. And whenever you have something like that, I'm kind of thinking, hey, is this maybe Pythagorean? But in this case, it's not, because these signs aren't squared. And so how could I maybe make it so that there's an expression with a 1 and a squared sign here? Well, the thing that we're going to do is, and this is pretty common, we are going to take this 1 plus sign in the denominator. We're going to multiply the top and the bottom by the conjugate of, I hope you're listening, the denominator. And so if we multiply both the top and the bottom by the conjugate of the denominator, the thing that I want to point out that happens kind of instantly is that on the bottom we get a difference of 2 squares. And so this whole expression now, instead of being over 1 plus sine, is now over 1 plus sine, 1 minus sine, which multiplies out to be 1 minus sine squared, which is awesome, because you guys, 1 minus sine squared falls in this Pythagorean identity box, especially 1 minus sine squared being cosine squared. And keeping our eyes open, that's something that we're actually working towards getting on the left-hand side. Now on the top, we have 1 minus sine squared times 1 minus sine squared. And there is something I want to say about that. When you take 1 minus sine squared times 1 minus sine squared, that's actually 1 minus sine squared squared. So in this case, we do have actually what we do have on the left here, which was a 1 minus sine theta in parentheses squared. The only thing we have remaining then to substitute for would just be to make a substitution in the denominator here and say that 1 minus sine squared is really truly a cosine squared of theta. And so we end up on the right-hand side having what we have on the left-hand side. We can go ahead and say then, here's our bridge, and actually I should be very, very proper about this, 1 minus sine of theta squared all over a cosine squared of theta. And so we did verify that these were equal. Now one thing I want to say before going on is just this 1 minus the sine of theta squared. If you were tempted to FOIL that out on the left here, you do actually have to write 1 minus the sine of theta times 1 minus the sine of theta. And the only reason I bring that up is because I get a lot of people trying to tell me that this is equal to 1 minus sine squared theta, because that would just be so tempting to have. And so these are not equal. If you FOIL this out, you would actually get 1 times 1 minus sine of theta minus the sine of theta, so minus 2 sine of theta. And then you would have a sine theta times a sine theta, both negative, makes this a positive sine squared of theta. So you wouldn't get anywhere near this difference of squares here. So just don't be tempted to do that. Okay. So number 3, I will tell you, out of all the examples we look at on this one, number 3 is going to be the oddest one. And so looking at the left and right hand side, I notice I don't have any squared trig functions with these ones. So these are not Pythagorean. And so it's kind of like, well, what side do I work on, and do I multiply by the conjugate here? And I'll tell you this happens, because both sides, not just one side here, had like a 1 minus sign, a 1 plus sign, but nothing was squared, but because both sides of this expression have ones in sums and differences with non-squared trig functions, I'm going to avoid actually multiplying by the conjugate in this one instance. And what I'm going to do is I'm going to work on the one side here that I feel is more complex just by the fact that it's a reciprocal trig function. And I'm tempted to rewrite these in terms of cosines. So that's actually the trick to one of these. We say 1 minus, and I know that secant is the reciprocal of cosine, so 1 minus the cosine of t here would be over 1 plus 1 over the cosine of t for that secant value there. And so I should put in extra parentheses there to show we made substitutions for our secants. But the thing here is this: on top and bottom, we are now adding and subtracting fractions, or subtracting and adding fractions respectively on top and bottom. And so we want to get a common denominator between these values here. So imagine this is a 1 over 1 on top and a 1 over 1 on bottom. Our common denominator on top and bottom would be cosine, or that is to say I would have to take the cosine of t on top and bottom times this 1 over 1. And so I'm going to do that both down here and up here. Now keep in mind I'm taking it times just this fraction right here. I'm not distributing it throughout the whole set of parentheses. So what follows then is this: we would get cosine t over cosine t minus 1 over cosine of t. And then this would all be over cosine t over cosine t for the other 1. And this would be plus 1 over cosine t. Talk about a complex fraction. So we're just going to simplify everything on top and bottom. And because we are adding and subtracting fractions with common denominators, that means everything on top now can be put over a single cosine of t. And we would just have cosine t minus 1 over that. So I'm going to write that. Go ahead and green write that here. So here's our whole numerator difference of those two fractions. And then in the denominator here, this would all be over a single cosine of t now, except for we would have cosine t plus 1 there. And so looking at it this way, we could say, well, now I'm going to multiply by the reciprocal because I'm dividing with fractions. But the neat thing is, keep in mind, look what we're looking for on the right-hand side, cosine t minus 1 over cosine t plus 1. When we rewrite this as the top fraction here, cosine t minus 1 over cosine t, that times the reciprocal of the denominator fraction, which is cosine t over cosine t plus 1. Okay. We're going to get our cosines of t to cancel, and multiplying straight across, we just get cosine of t minus 1 over cosine of t plus 1, which is exactly what we needed to show here. And I'm lazy because I didn't rewrite it again, but I just wanted to show you that this is going to be the one example I would tell you where I wouldn't multiply the top and the bottom on either of these sides by the conjugate of the bottom, but because they're unsquared trig functions with ones on either side. Okay. All right, so let's look at a few more examples. Number 4. I got to tell you, I actually do get really excited about multiplying by conjugates. And it sounds really stupid, but see, I look at this in this case as not a couple of fractions with just unsquared trig functions and ones on top and bottom. And so in this case, I'm less leery about multiplying by the conjugate, excuse me. And so I'm going to do that here. I'm going to work on the right-hand side, and I'm just going to choose to multiply the top and the bottom by the conjugate of the bottom, always the conjugate of the bottom. And so this would be, the conjugate here would be secant x plus 1, and I would have to do that on top and bottom. Secant x plus 1 on top and bottom. So what follows then is I get this. I get tangent x times this, in parentheses, secant x plus 1 on top. But on bottom, what I get is a difference of squares, and not just any difference of squares. I get secant squared x, and this would be minus 1. Now, looking at my identities here, I have a secant squared x minus 1 coming out to be the same thing as a tangent squared x. And so the neat thing here is then, well, this is Pythagorean, and I can make a substitution. And if you might be thinking to yourself, how is this going to help me here? And why didn't I go ahead and distribute the tangent x on top? Why is he leaving it outside the parentheses? The reason why is because when I make this substitution here, the tan squared x down here, that has a common factor with the top, which is also its tan squared x. And so we can cancel out this tan squared of x, or this tan of x with one of these tans of x. And what follows then is we get left with secant x plus 1 over the tangent of x. And, of course, keeping in mind that that's what we're working toward, you could see that that worked out really well just by multiplying by the conjugate. So I can't tell you enough how much multiplying by the conjugate is a very useful thing in given circumstances. Okay, so looking at the right here, sorry, the number 5 that is to the right of number 4. The right-hand side looks more complicated to me. So I'm going to go ahead and proceed with it. And just because I'm telling you that I get really excited about multiplying by conjugates, I'm going to do that again here. So let's go ahead and try to take the top and the bottom here times secant x plus tangent x, which would be the conjugate of secant x minus tangent of x here. And what we would get on top is just anything times 1 is itself. I suppose it follows that we would get secant x plus the tangent of x. And on bottom, we would get a difference of squares, secant squared x minus tangent squared x. Now, in terms of this being now of a squared type, could we make a Pythagorean substitution? Secant squared minus tangent squared is actually the same thing as 1. So in this case, we actually get secant, beg your pardon here, secant of x plus tangent of x on top. But on bottom, we can go ahead and substitute in a 1, and of course anything divided by 1 is itself. So it follows that the top here is the only thing that gets left, and that is just rad, because we have secant x plus tangent x on the left-hand side also. QED. All right. So looking at number 6, finally something that doesn't have ratios on either side. And so I'd say, what kind of algebraic techniques would I be persuaded to use here, and of course which side would I work on? You know, the left and the right hand side are kind of equally complex, but the thing that gives the left hand side the edge is that these are fourth powers. I feel like that's just serious business. So fact is though, these form a difference of squares, and the neat thing about having these being fourths is that when I factor it, they become squares. Sine squared x minus cosine squared x. Actually, I'm going to put plus first. I just like the plus first here. Sine squared x minus cosine squared x. And of these two factors that we would just algebraically manipulated this into a product of, we could see that sine squared x plus cosine squared x is just 1. And so in this case, we actually just get left with sine squared x minus cosine squared x on the left. Now, this is not Pythagorean in nature just because it's only sine squared plus cosine squared that equals 1. We could never form sine squared minus cosine squared of x. So in that case, I feel like I'm kind of stuck, and maybe that I'd want to go work on the right-hand side, but the thing here is on the right-hand side, I don't have a lot to work with either. I just have a cosine squared that maybe, you know, looking at my identities, cosine squared, I could go plug in a 1 minus sine squared, and that would be helpful. So I'm going to stick with the left-hand side, and I'll tell you the thing that it is that I'm going to do here is this. I'm going to notice that if I want to go from this expression on the left to the right-hand side, I need to lose all my signs in the expression. It needs to just be cosines. And so what I'd be looking to do is make a substitution for sine squared, and that's the case here. If you substitute for sine squared, because sine squared plus cosine squared is 1, then sine squared is always, of course, 1 minus cosine squared. So I am going to go ahead and make that substitution here, 1 minus cosine squared x, and this would be minus another cosine squared x, but combining like terms now, a negative cosine squared and a negative cosine squared, then it would follow that we would get 1 minus 2 of those cosine squareds of x, and that's great also because we wanted to get 1 minus 2 cosine squared of x on the right also. Okay, so we've seen some factoring, we've seen multiplying by conjugates here. Let's take a look at these last two examples. So number 7, I really feel looks a lot like this first one we did here in that there are two terms in this expression and they both have a secant. So perhaps we work on the left-hand side, perhaps we factor out this secant of a, and what we would get left with is a 1 minus a sine squared of a. And so in this case, this having a 1 and a squared trig function, I'm tempted to call it Pythagorean. Looking at our identities here, 1 minus sine squared is always cosine squared. So let's go ahead and rewrite this again as the secant of a, but instead this time as a substituting in a cosine squared of a, we look at it this way. And so what else could I do with the left-hand side? Well, you know, multiply these things, but they're really not going to cancel anything until we rewrite our secant as the reciprocal of cosine. So maybe we try rewriting everything in terms of sines and cosines as we have been and see if we can get anything to cancel. Well, my cosines of a, at least one of them cancel out, and I get left with a single cosine of a. So QED, we were able to get our logic to follow here. Let's take a look at this last one. So number 8, man, the two sides, what side are we going to work on? Probably the left-hand side. So let's go ahead and get started on number 8. Looks like, what are we doing with these things? Well, a few things we can do. One thing we could do is we could rewrite cosecant and secant in terms of sines and cosines to see if that would be very helpful. But we're also adding two fractions, which means we could get a common denominator and stick these things together. I will tell you, I can already know which of those two is the easier of the two to do here. And I'm going to tell you, in this case, it happens to be rewriting in terms of sines and cosines. So I'm going to go ahead and pursue that way just with you here, just to kind of be a testament to sometimes rewriting in terms of sines and cosines is a helpful thing. But I would get sine over 1 over sine of x plus the cosine of x over 1 over cosine of x. And what ends up happening is we have to multiply both of these by their own reciprocals, and so we would say of their divisors, excuse me. But sine of x times, I suppose, sine of x over 1 plus cosine of x times cosine of x over 1 would actually have this statement follow: sine squared x plus cosine squared x. And the reason why I wanted to chase after that is because I knew I wanted to get a 1 on the right hand side. So I'm going to substitute in a 1 here, which is the one we have on the right, and we could just build our line of logic, but this is B what we get here. So hopefully these help you get through the remaining exercises there. But remember, try factoring, try multiplying by conjugates, try adding and subtracting fractions and getting common denominators. Cheers.